Hello and welcome. In this video, we'll be diving into the world of logarithmic functions. Our main goal, or learning objective for today, is to understand and be able to identify the key characteristics of these powerful mathematical tools. By the end of this lesson, you will be able to identify the key characteristics of logarithmic functions. We'll explore several key properties, including their domain and range, their increasing and decreasing behavior, how they transform, and their vertical asymptotes. Let's get started. First, let's understand what a logarithmic function is. The key to understanding logs is remembering their connection to exponential functions. Logarithmic functions are the inverse of exponential functions. Remember what an inverse function does. It reverses the input and output. For exponential functions, we input an exponent and get an output. For logs, we input the output and get the exponent back. In other words, the equation a to the y power equals x is equivalent to the logarithmic statement log base a of x equals y. They both express the same relationship in a different way. This inverse relationship is why logarithms have a very specific domain and range. That's our first key characteristic to identify. Our first topic is the domain and range. These tell us which x values are allowed and what y values are produced. We'll focus on the domain and range of logarithmic functions. Let's recall the domain and range of its inverse. The exponential function f of x equals a to the x. The domain is all real numbers, and the range is all positive real numbers. Because logarithmic functions are inverses, their domain and range are swapped. The domain of a logarithmic function is the range of the exponential function, which is all real numbers greater than 0. The range of a logarithmic function is the domain of the exponential function, which is all real numbers. This means a logarithmic function will only accept positive inputs. You can't take the log of 0 or a negative number. Let's visualize this. Here we see the graphs of an exponential function and its logarithmic inverse. Notice how the log function only exists for x values greater than 0, but it extends infinitely up and down along the y-axis. The domain is positive numbers, and the range is all real numbers. Next, let's explore the increasing or decreasing behavior of logarithmic functions. The second characteristic we'll look at is their increasing/decreasing behavior. Remember, the base a is key. This behavior depends entirely on whether the base is greater than 1 or between 0 and 1. When the base is greater than 1, like in the graph of y equals log base 2 of x, the function is always increasing. When the base is between 0 and 1, like in the graph of y equals log base 1/2 of x, the function is always decreasing. This means a logarithmic function will never change direction. It's either constantly going up or constantly going down. Because of this, they do not have any relative maximum or minimum values unless you restrict their domain to a closed interval. They also do not have what's called points of inflection, where concavity changes. Now, let's talk about how we can transform these functions. Specifically, we'll look at additive transformations. Our third topic is additive transformations. A common transformation you'll see is a horizontal shift. This occurs when you add or subtract a number inside the logarithm with the variable x. A horizontal shift changes the input values, but it does not change the fundamental logarithmic nature of the function. For example, consider the function y equals log base 3 of x plus 2. The addition of 2 inside the parentheses shifts the entire graph of y equals log base 3 of x to the left by 2 units. This transformation also shifts the domain and the vertical asymptote. The new domain becomes x is greater than -2. The key, however, is that the function still behaves like a logarithm. Finally, let's discuss one of the most defining visual features of a logarithmic function, its vertical asymptote. We will now examine the vertical asymptote and end behavior of logarithmic functions. For the general form y equals log base a of x, there is a vertical asymptote at x equals 0. This means the function approaches the y-axis, getting closer and closer but never actually touching it. This is a direct consequence of the domain x being greater than 0. Let's also talk about the function's behavior as x approaches this asymptote and as x gets very large. As x approaches 0 from the right side, the function's value becomes unbounded. For a base greater than 1, it goes down to -infinity. As x increases, the function does continue to increase without bound, but it does so very slowly. For example, log base 10 of 10 is 1, but log base 10 of a trillion is only 12. It takes a huge change in x to get a small change in y. Let's quickly recap what we've learned and seen today. We set out to identify key characteristics of logarithmic functions. We learned that they are the inverse of exponential functions. We saw that their domain is restricted to positive numbers, and they have a range of all real numbers. We observed that they are always increasing or always decreasing, depending on their base, and they are either always concave up or always concave down. We discussed how transformations can shift their graphs without altering their fundamental logarithmic nature. And finally, we identified their defining feature, the vertical asymptote at x equals 0, and their slow but unbounded growth. I encourage you to pause and think about each of these points to solidify your understanding. I hope this overview has helped you better understand the key characteristics of logarithmic functions. Thank you for watching.